I've known Ingo for several years. We met at several conferences. We met, I think, in Savannah in 2006 at an NSF workshop on reliable engineering computing for the first time, then at SCAN 2006 in Germany, and probably at several other conferences. And don't be scared by the word Geodetic. He's actually working at Leibniz Institute of Hanover in Germany, in Geodetic Institute, but he's not the person who is running around trying to figure out. He's the one who processes the data. So he will be talking about a lot of things about uncertainty and everything, and while his application is geodetic, in principle his methods are useful in all places. He is here. If you have any questions and you miss him right now, he's here until March 22nd for 3 more weeks. He's sitting in Trek's room, so please welcome to come and see, and he will be very eager to collaborate, to do something today. So let's welcome.
Thank you very much. It's a great pleasure for me today here to present my talk, and many thanks to the department, especially to Professor Krajinovic for making this visit here possible. So what I'm going to talk about is some uncertainty modeling in geodetic application techniques and challenges. This study is together, or was carried out together with Hans-Jörg Kutterer. He's the head of this institute. Before I start with the main topic, just a few slides about where I'm working and what we are doing there. That's the main building of our university, and this is located nearby. It's our institute, the Geodetic Institute, and Hanover is located in the northwest of Germany, in Central Europe. Our main research area, as Static said, is data processing and data fusion. So the example we worked with for deformation analysis, what means we observe buildings and compute point coordinates for this building to detect significant changes between, let's say, between the year 2000 and the year 2004. Another example, we have special sensors that allow us to map three-dimensional objects very fast. Example, a laser scanner or tachyometers here. And the aim is now to process the data to reconstruct the buildings, what I think it's called here reverse engineering. And another example is that we bring some sensors together to some sensor networks or to platforms. And here's an example with the laser scanner. The laser scanner is moving, and it is registered with the help of GPS and inertial measurement units. As the main part, or I think all these tasks, the data processing parts, are, in my opinion, in a close relationship to computer science and to applied mathematics. And what I'm going to talk about in detail is now deformation analysis, how we process the data, describe the occurring uncertainties, and so on. And therefore we need especially well-founded decisions if there were significant movements in a building between two epochs. So decision making is the main point, especially here statistical tests. When we started to describe uncertainties with the approaches that Static also uses, because sometimes the uncertainty is too optimistic, is underestimated in our applications. And I want to highlight this with an example. We have two different techniques to observe, example, a building. We can on the one hand take terrestrial measurements, example, measuring distances and so on. And on the other hand, we can do satellite measurements, example, GPS. And the estimated uncertainties from the residuals after an adjustment fit very well if we only use one of these techniques. If we combine both of these techniques, the uncertainties are too optimistic or underestimated. So, and this is, in our opinion, due to the ignorance of non-stochastic errors or due to interval errors in the measurement and in the pre-processing steps. Let's have a look at this figure here. It describes the interaction between observation models and analysis models. And an analysis model can be, example, least squares adjustment.
I'm sorry, you're saying that when you combine the two different error sources, that that's too optimistic. Is that because the two error sources are somehow correlated? No. So rather than having two independent.
So the answer is yes.
Okay.
Because when people combine, they assume that they are independent without thinking. That's what they are taught in introduction to whatever it is, engineering, physics, to do. If you have two measurements, you combine them, you assume they're independent, yes, but they're not independent.
Okay, it describes the interaction between observation and analysis models, and an analysis model can be, example, a least squares adjustment. We were assume in this model that all distance measurements are made at a temperature of 50 degrees. But the observations are not made at a temperature of 50 degrees. They are made, an example, at 30 degrees. So we have to pre-process these measurements in order to fulfill the assumptions made in the analysis model. And therefore, one can use some additional information, example the temperature, to model the velocity of an electromagnetic wave propagation, and then the parameters that reduce the uncertainty due to because of some special instrumental error sources. And the last point here, some model constants, example the group reflection index and the formula of Barrel and CS. And these influence factors, let us call this influence factors, cause some non-stochastic errors or interval errors. And this is meaningful due to many reasons. Example, the model constants are only partially represented for the given situation. The number of additional information of the temperature, pressure measurement is too small to estimate reliable distributions, therefore, and we have displaced measurements that are affected by rounding errors. And other non-stochastic errors occur if we neglect correction and reduction steps or effects that cannot be modeled, example between reality and our model. So, after this short motivation, I'm now going to describe how we model these occurring uncertainties and how we propagate them to some parameters of interest, and then we have a look at statistical tests, how we can check the accordance of the collected data with the assumptions met in the model. And after this, the talk ends with some applications and with challenges and future work. So, that's only a short reminder. As said, we have two types of uncertainty. On the one hand side, stochastic or probability uncertainty, and on the other hand, interval or imprecision, called here as interval errors or fuzzy uncertainty, to describe the non-reducible effects during data processing. And our main idea is to describe these influence vectors with intervals or fuzzy sets or nested sets. Here's a fuzzy number given with slash and reference function, and a very important notation or definition is here the so-called alpha cut. And different alpha levels represent a different degree of belief from experts, maybe from some experts in the context of nested sets, or only from one expert. And the alpha level of 0 can, example, be a guaranteed bound for this. But guaranteed bounds often lead to overestimation, or sometimes lead to overestimation of the uncertainties. Therefore, we introduce here some alpha levels that represent different degrees of belief from the expert to have more realistic uncertainties after propagation, after propagating the uncertainties. So what's the formulation of the problem? We have some quantities that are given with uncertainties, non-stochastic uncertainties, and we have some parameters of interest. Let's say, for example, a point coordinate of a building, and that these parameters or quantities of interest are a function of these quantities with given uncertainties, where f is a known algorithm or function. The first goal is then we must propagate the uncertainties from these quantities here to the quantities of interest. And the second goal is we have to carry out statistical tests, especially hypothesis tests for these quantities in one and multidimensional case. And therefore we assume that the function here can be approximated with the first Taylor series. This is standard in basic application because the uncertainty of the measurement is much smaller than the measurement itself. So let's come to the first goal. We want to propagate the uncertainties from these influence factors, temperature measurement, pressure measurement, uncertainties of the instrument, to the quantities of interest. As I said, we can linearize it without losing important information. So we have here the uncertainty of the parameters of interest, or the parameters of interest, with the matrix of partial derivatives and the imprecision of these influence factors. And when we construct the fuzzy set or the nested set for these quantities of interest, we have a stochastic midpoint that is superposed here by this imprecision, computed in terms of alpha discretization. So we evaluate the uncertainties for each alpha cut within a linear propagation here. In case of intervals, it's very easy. We have only to use one alpha cut, then we obtain the solution with the radius, with the lower and with the upper bound. And let's come to the second goal of this talk here. How can we now check the accordance of these parameters of interest with the assumptions met in a model? What we need is statistical tests, and especially in parameter estimation, global test, outlier detection, congruence test. Congruence test means we have two parameter sets, one example in the year 2000 and one in the year 2004, and we want to check if they are identical. Then in model selection, we have to select a suitable model to describe the data, and we must use sensitivity analysis, what means we have to check if our model is able to detect movements, or example, bandwidth of parameters.
Question?
Yes, true.
Sorry, maybe I missed or maybe I misread. Type 1 error is that a false positive or a false negative?
If you reject the null hypothesis, also it is true. That is, for me, a type 1 error.
So type 1 is a false negative. You reject it when it's true.
Yes, exactly. Yes.
Okay, so then type 2 is you accept it when it's false.
Yes, exactly.
Okay, so why does model selection only fall into type 1 error? I would think all of these things would be for both type 1 and type 2. Why do they split?
Yes, in geodesy it's more typical to use only here model selection, but because we don't know the alternative hypothesis, so it's more adequate to use only the null hypothesis, and there we can only use type 1 errors. So in the case of observation, we only have one, or let's speak in the pure stochastic case, we have an observation, only one number, and want to compare it with the distribution of the null hypothesis, without any knowledge about an alternative hypothesis. So we can only use the type 1 error, and this is the case in geodesy.
actually a typical statistical situation when you, and this is something that people in decision theory, where is Francois, whom we need here, have been struggling for 60 years and still haven't beaten them. Because what they do is they have, this is null hypothesis, we know nothing about anything else, and we need to make a decision. And so basically, the logic behind this is the following. Suppose you have like a population. If anybody has a temperature higher than something, that's suspicious, so we need to make additional tests to figure out what's wrong with that person. So what do? Ideally, we should have perfect, like with astronauts in the orbit, we should have perfect health care for everybody. You walk into the doctor's office and say, you know what, I sneezed today. Immediately the whole battery of tests, MRI, whatever it is, to check. In reality, you cannot afford to do that, and therefore you have to limit it to only a certain percentage of people. If you can only afford to do tests for 5% of people, that's what's most important, type 1 error. So the people who are in reality healthy but have to undergo the tests should be limited to 5%, because if we do it more, then we completely run out of money for the federal government. That's the same thing in geology, because there are, we are talking about rare situations. It's not like things are falling apart. All this is done to prevent the buildings from being damaged. So this is done on every building, and only if we do something, if there's a very rare case when something is suspicious. Again, we don't stop the building, we don't evacuate, we do additional measurements in order to make sure that this building is indeed safe. So our main concern is not so much not to miss the building which is falling apart, it's more to avoid spending a lot of time on doing extra work on bridges and buildings which are absolutely safe already.
And these decisions are based on...
It should be type 2 errors.
Thank you. These decisions are based on statistical tests, and therefore I want to introduce our idea how to model statistical tests, statistical hypothesis tests in case of imprecise data. Therefore, let's have a look at the pure stochastic case first. There we define a region of rejection, acceptance, and the exact value of the test value is compared with the region of rejection, and we have it is either element of the region of rejection or region of acceptance. So we have here a clear and unique decision. But if we take non-stochastic measurement of certainties into account, we have no more only one number here. We have, example, a fuzzy set, and this is due, in our case, due to the imprecise knowledge of the influence factor. And if we do not know the type error exactly, because no expert can say with the type 1 error is at 5%, maybe at 1%, so we introduce the transition region, fuzzy type 1 error, and the region of rejection is then given as the complement, so mathematical complement of the region of acceptance. And as one can see here, the test value is in general an element of the region of rejection and also here the region of acceptance. So how can we decide if we reject or accept the null hypothesis? Therefore we need the comparison set, and we need at the end, because we have to make a decision as engineer, a precise criterion pro or non-acceptance and probabilistic interpretation of the results. The main idea is to check the degree of agreement of the test value with the region of rejection, and to check the degree of disagreement of the test value with the region of acceptance. And therefore we can use two types of functions. From the computational point of view, very easy to compute function is the height of this intersection, and a more realistic one is the cardinality of this. And both of these functions vary between 0 and 1. The final degree of rejectability of the hypothesis is now computed with a t-norm. There we can also use other t-norms or s-norms, but we choose here the minimum because first we discussed this in case of outliers, and therefore we need a strict a strict degree of rejectability, what means that the test value has to be in the region of rejection and has not to be in the region of acceptance, and that is the case when we use here the minimum rule. The test decision is then based on the final comparison of the degree of rejectability with the value rho fit here, that is element between 0 and 1. If it's smaller, then we do not reject, and otherwise we reject. How can we choose this critical value? I have here two examples. The first case is an outlier detection. Due to the reason that we have an extended uncertainty budget, the element here, the test value, can also be in the region, or is also in the region of rejection. We shall not reject the test, so we have to choose rho crit near 1. Otherwise we have, and do not reject in this case then, if we choose it near 1. And otherwise, other case can be, we have safety relevant. Example, when we have to be sure that the building can or shall not move, or does not move, we have to choose here this value near 1, and in this case we reject. Here's the geometric interpretation of these two criterions. The first is the height, compute the degree of agreement with the region of rejection. This is given in red here. The degree of disagreement between the test value and the region of acceptance is the blue one. And then the minimum of both is the degree of rejectability that has to be compared with this critical value. The second one, and I think it's a better one, but from the computational complexity it's more computationally complex. We have here the area, the cardinality of the test value with the region of rejection, the cardinality is the region of acceptance, and then based on these two areas we can compute the degree of rejectability, and this is the minimum of both, and compare it, and so on. Here are two examples. Test value with weak imprecision, and both degree of rejectability are given here. The blue one is the CARD criterion, and the red one the height criterion. So every bit means we compute for every midpoint here the degree of rejectability. The midpoint is here, the degree of rejectability is here, and the midpoint is here, we find the degree of rejectability here, and so on. Second example, and there I want to highlight why we prefer the cardinality. We see here the degree of rejectability for the cardinality, and here the degree of rejectability for the height criterion. And also we have here strong uncertainties. In case of the height criterion, we cannot reject it when the midpoint is inside here the core of this fuzzy set. This was the one-dimensional case in testing, and we want to see now how the multi-dimensional case can work. And therefore we have also, or we can answer 4 of these questions with a linear hypothesis. So this is where we are known, where we only have stochastic or probabilities for the measurement. Here we have the equation of a parameter estimation with the normal equations, with the observations and the approximate values of the observation, and we assume here what I think is straightforward, that the observations are normal with a given expectation and a variance covariance matrix. Then the second step is that we introduce a linear hypothesis, an example where a combination of the parameters is equal to the vector W here under the null hypothesis. And this leads, after a few calculation steps, to a quadratic form here given that follows under the null hypothesis chi-square distribution with h degree of freedom. The test decision is then easy. We can compare the test value with the practical value of this distribution. But in case of imprecision, we have no more this precise value for the test value. We have an imprecise one, and so we have to introduce this function here, as what I said at the beginning of the talk, some parameters of interest. Here an example, these parameters of least squares adjustment are a function of some measurements or influence factors. And if we introduce this function here into this quadratic form, we use here x is equal to a transpose and so on, then we obtain this quadratic form that we can solve with alpha-cut optimization. Here's an example. Here we have some imprecise quantities for each alpha-cut in an interval, and so we construct for each interval the resulting alpha-cut of the test value. We have a matrix function, and we have to use then, or we have to search for the minimum and the maximum of this mapping function. And this is a quadratic optimization problem, and this is given in standard software tools. Here's the final test value. So the multidimensional case is reduced to the one-dimensional case, like in the pure stochastic case, and we can now compare the test value with the region of acceptance and rejection, as I told on the slide before. So I think we are running a bit out of time. So I'll skip the probability of type 1 and type 2 errors. We have with this test, we have the possibility to compute the probability of type 1 and type 2 errors also. And so I'll continue with some examples for us. Here we see a log where ships are passing through, and due to the changing water levels inside this log, we have deformations. Example here with this wall. And therefore, we use a monitoring network with some stable points around this log here, and some points that represent the deformations on top of the log. They are here, here, and there. So the aim is now to get the deformation of this object. And here are the uncertainties of these influence factors. The temperature is imprecise with 1 degree, the pressure, and some special error sources, instrumental error sources, and that leads to the uncertainty for the observations. For in case of standard deviations, we have for direction measurement, or let's have a look at the distance. We have distance 3 millimeters, and at the alpha level of 0, and a bar uncertainty of 0.5 millimeters. The control network was determined with 313 observations, and the aim was to compute the 45 parameters that are the coordinates of the network, and due to the large number of observations, there may be outliers in there, and we have to remove these outliers from the data material because the outliers may falsify these point coordinates. And here's an example of such a test. A multiple test for 5 direction measurements, and the fuzzy regions for the type 1 error here that are from 5% to 1%. And what we see is that we have, in case of outside detection, a very weak imprecision. And this leads, when we compare the test value with the region of acceptance and rejection, to a degree of rejectability of 0.16. And in case in outside detection, when the null hypothesis is not rejected, in case of a safety relevant application, we will reject it. Here's another example, and there we see that uncertainties and non-stochastic uncertainties become more and more important. It's a congress test, so we compare this network first measured in 2000 and then measured in 2004 with each other, and check if they are identical or if there are some significant movement of the log between these two epochs. And due to the computation of the sum of the difference, the non-stochastic ones become more and more important. We can see this here with the transition region or the fuzzy region for type 1 error with 5% to 1%. It's the same as in the first example. And we see that the bandwidth of this test values here much larger than the transition regions, and therefore we have a strong imprecision. In this case, if we compare it with the region of acceptance and rejection, we have a degree of rejectability of 0.52. And this is a very important result for us, because as I said at the beginning, that we have problems if we bring together two techniques of measurements, the terrestrial and the satellite measurements. And here's the same, we bring two epochs together, and the uncertainty is much stronger. So maybe this is the reason for that the uncertainty is underestimated if we bring the two techniques of measurement together. Or we can model this underestimation better, and have a more realistic uncertainty budget. Do we have how long can we
Well,
speak?
normally we have to end at 2:30, but
Because there
Okay, it's okay.
there are people that, if we want to, we can take a break in those people.
no,
I can-
it won't help. It won't help. No, break is a bad idea. Because we have meetings with TAs right now, and then the TAs have to go to the TA meeting at 3 p.m. sharp. So it's,
I just run
Okay.
across campus right now.
I skipped the type 1 and type 2 errors examples, and so if anybody is interested, I'm grateful for any discussions about this in the room.
If people want to meet with you, where would they find you?
In the
124, Drexel.
125.
124.
Okay.
The door is, well, it may say one. I'm sure it says one.
If you're looking for 124 and he's in 125,
I think people will figure it out. No, there's one room, and legally speaking, when you sign for the key request, it always says computer science 124.
But
The sign on the door may
happens to
say
go to that one
125.
too.
Yeah, I think that there are two signs on the door.
It's in front of the candy machine.
Sorry?
In front of the candy machine, you can find him.
Okay.
Okay, let's come to the conclusion. We have here shown some statistical tests, and you've not seen that it's possible to compute type 1 and type 2 errors, but it's possible. And also the non-centrality parameter can be computed in the imprecise case. The 1D case is straightforward. For the multidimensional case, we have to reduce it to the one-dimensional case, so we need hypercut optimization. And the CART criterion was more adequate or more realistic than the high criterion. And the difference between the precise and the imprecise case depends on the task. And so if we have outlier tests, we have a later rejection of the null hypothesis. In our examples, if we have safety relevant tests, we have an earlier rejection if we take non-stochastic errors into account. And also the tests depend on the order of magnitude of this non-stochastic error. At the moment, we are processing some data for assessment and validation, an example for the critical value, and we make some work to reduce computational complexity. Some challenges for the future will be to apply these procedures for a posteriori variances, for nonlinear state estimation, and also to work with nonlinear function, because now we only linearize this function between the quantities and the quantities of interest by first Taylor series. And what we also want to take into account is object fuzziness, what means that the object itself may change over time due to temperature of the material. Okay. Some acknowledgements at the end of the talk to the German Research Foundation who founded this project, and thank you for your attention.
Let's have a few questions, comments, suggestions. I can also add that we are working with Ingo on the other aspect of that, because this is kind of, let me put it this way, to engineers, statistical method is what? Bumper jump, right? They look at the textbook, they see the chi-square, whatever it is criterion, they use it, they don't know where it comes from, they think it's the only criterion that has always been used. So, since we are going further, since we are kind of taking into account intervals and other uncertainty, of course the important questions are the ones which were raised by several people here, sitting by Steve, for example, right? Which is, why the heck, right? Why do we use this method? Why do we use that method? I mean, if you study statistics deeply, you know there are tons of criteria, and the ones that are used, they're usually used well for kind of historical reasons. Pearson said that, or whatever it is, or Fisher proposed this method, and this has been traditionally used, and people use it without thinking why it is the best. They're using it because if they use this particular Pearson or Fisher's criterion, then kind of it's acceptable, and it can be compared with other results. But since we're venturing outside, we don't have to be bounded by this method necessarily. Same thing with data processing on the fuzzy data. Again, people do what? People take the MATLAB package with fuzzy, okay, so let's do it. Click, 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 get some results, publish it. Another person selects something else, click, 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 publishes some other results of processing the same data. Just like with statistics, there is no guarantee that you will get exactly the same result. What we would like to do is to get some reasonable foundations, and that's, I think, one of the objectives of why Ingo is here, just to kind of to get a general understanding why these methods are used. They seem to be working well in practice. The only motivation is computational simplicity. It's not such a big deal nowadays. You could run more sophisticated tests, so why use these ones? And we are making some progress here, and he did present a more technical paper with a longer paper at the recent conference on Geodetic in Savannah. So I think we are getting something, but again, this is the area which should not be, if you're thinking, okay, geodesy, I'm not interested in that. Statistical analysis is something that people use all the time. Those of you who attended my talk, you may relate. If you don't relate, I'm just telling you, the only thing is that different is that I use different notations, different variables, but basically I was talking about the same type of problems. You have some data with uncertainty, you need to process it, right? And so here is a partial example on the question asked by Dr. Longpre. I'm a poor gradient student. How can I use that in real life? Well, this is one real life application of this interval and other uncertainties combined with probabilistic ones. So I'm not saying Ingo is a poor gradient student, but kind of he's a very well off graduate student.
Okay. This is a case, this is a real world problem
Yep.
where these techniques matter.
So thank you.
Okay.
And